Before we conclude this unit of study on periodic motion, and in particular simple harmonic motion, I want to take some time to go through a few example problems that might illustrate the principles that we've developed so far in these video lessons. So here's a graph of acceleration versus time for some mass spring oscillator. And we're going to assume this is the mass spring oscillator on a frictionless surface, where the period is equal to 2 pi times the square root of m over k. And I don't think it's been pointed out yet that it doesn't have to be motion on a horizontal plane on a frictionless surface. The exact same behavior occurs if the spring hangs vertically with some amount of mass attached to it. Whatever length the spring comes to under the influence of gravity when the mass is attached is our equilibrium position. Now here we might use the symbol y instead of x for position, but the oscillations are just the same, simple harmonic. And so whether or not a graph of vertical position versus time looks like a graph of cosine, or maybe sine, or maybe even a graph of negative sine, all of that really depends on the moment in time that you start observing the system that's oscillating. So here we're given a hypothetical case where the graph of acceleration versus time takes on a shape that's, well, it's not exactly a graph of sine, cosine, negative sine, or negative cosine. In general, we can describe the motion. Let's go back to the case of the one oscillating on a horizontal plane. We typically say x equals a cosine omega t. But really, depending on when we begin observing it, more generally we can say x equals a cosine omega t plus phi, where phi represents something we call the phase angle or the phase shift, which allows our graph to be shifted to the left or to the right depending on the location of our origin in time. Here are the questions based on this graph. Number 1, at what point or points is the position of the object negative? Let's use some equations to guide our thinking. F equals ma. Net force is mass times acceleration, and the net force, as long as there's no friction, is governed by Hooke's law. So negative kx is equal to ma. So a equals negative k over m times x, which means a equals negative k over m times amplitude times cosine of omega t plus phi. Meanwhile, x is equal to positive a cosine omega t plus phi. This means that acceleration and position are 180 degrees out of phase due to the fact that one equation has a negative sign and the other has the positive sign. So, you know this, if we pull the object back and abruptly set it into motion by releasing it from rest, then at the moment we first let it go, the acceleration vector is going to point to the left to try to bring it back to the equilibrium position. But at that moment, its position, x, is positive. So acceleration is negative when position is positive, and vice versa. As soon as it goes past the equilibrium point, then even if it's moving, even if its velocity vector points to the left, its acceleration vector points to the right. So the acceleration is positive for any moment that the position is negative, 180 degrees out of phase. So to determine when the position is negative, we just need to figure out when is the acceleration positive. And there's only one point, that's position number 5 on our graph. Next question, at which point does the object have the greatest positive velocity? So let's just see if we can identify some of these points. I'll clean up my act a little bit here. So when does an oscillator have its most negative acceleration? That would be when it has its most positive position. Let's draw 3 positions of the object at equilibrium, when the position is most positive and when position is most negative. So when our object has an acceleration that points in the negative direction at its greatest value, that would correspond to this position. When the object moves from that point forward in time, next thing you know, it's here, and the acceleration is still negative, but not as great in magnitude. So this would correspond to position 3. Position 4, now it's moved on even further, and it gets to the equilibrium point, and at that moment in time, the acceleration is 0. So this point 1 on the graph must correspond to a moment in time just a little before it has returned to this position, right? So in any case, in this position, the velocity is 0. In this position, the velocity is in the negative direction. It's moving to the left. As it passes through equilibrium, this data point on the graph, its velocity is to the left. So the only position where it would have a velocity to the right would be position number 1. Grab your calculators, follow along. A 750 gram mass is attached to an ideal spring, and it oscillates across the frictionless surface. We can call that 0.75 kilograms. And the equation is given as x equals 0.24 cosine of 12t. So immediately we recognize that the amplitude is 24 centimeters. Our general expression is x equals a cosine omega t plus phi. So we also notice right away that phi is equal to 0 degrees. So a graph of position versus time will look like a perfect cosine graph. So we've already answered part 1, what's the amplitude of the system? 24 centimeters. Now we're asked in question number 2, what's the stiffness of the spring? Well, another thing we identify right away is that omega is equal to 12 radians per second. We're going to assume MKS units for the values given in this equation. But we also know omega is the square root of k over m. So if we square both sides of that equation, omega squared is k over m. This means that we can find the stiffness of the spring by multiplying the mass times the value of omega squared. We were given the mass as 0.75 kilograms. Omega is 12. 12 squared is 144, and 144 multiplied by 0.75 gives us an answer of 108 newtons per meter. What's the maximum speed of the system? We can take the derivative of this expression with respect to time. If position is a cosine omega t, then velocity is negative omega a sine omega t, and then the maximum speed would then be omega a. So we have the value of omega, it's 12, we have the amplitude, it's 0.24 meters, so if we multiply, we get V max is 0.24 meter times 12 radians per second. Radians just disappear when we combine them with other units, and so we're left with units of meters per second, and that works out nicely. 12 times 0.24 gives a value of 2.88. How much total energy is in the system? We've got a couple ways of answering that question. The total energy is the same thing as the maximum kinetic energy. which is also the same thing as the maximum potential energy. The kinetic and potential energies don't reach their maximum values at the same amount of time. When the object is fully stretched, kinetic energy is 0 and potential energy is a maximum. When the object's at the equilibrium point, kinetic energy is a maximum and potential energy is 0. So the energies cycle out of phase with each other, but their maximum values are equal to one another. So which do you prefer? The maximum kinetic energy is 1/2 mass times maximum velocity squared. Maximum potential energy should be 1/2 k times maximum position squared. And we have all the information we need to calculate either way. So let's try both approaches. 1/2 times 0.75 times 2.88 squared versus 1/2 times 108 times 0.24 squared. So let's try the first one. 2.88 squared multiplied by 0.75 divided by 2 gives an answer of about 3.11 joules. 0.24 squared multiplied by 108 divided by 2, not surprisingly, gives an answer of about 3.11 joules. This time, our oscillator is 0.8 kilograms. It vibrates with an amplitude of 0.3 meter and has a total energy equal to 67.5 joules. This means 1/2 m Vmax squared is equal to 67.5 joules, or 1/2 k times amplitude squared is equal to 67.5 joules. So our first question is to determine the stiffness of the spring. Well, we could go ahead and use this formula then, right? We know the amplitude is 0.3 meters. We know the total energy of the system. So you have to solve for k. If we rearrange the equation, if 1/2 k a squared equals energy, then 2 times the energy divided by amplitude squared is equal to k. So 2 times 67.5 divided by 0.3 squared gives a value of 1,500 newtons per meter. What's the maximum speed of the system? Well, we have the mass and we have the total energy. So now we can use the formula 1/2 mv squared. So if 1/2 mv squared is equal to the total energy of the system, then 2 times the energy divided by the mass is equal to the velocity squared. So the velocity is the square root of 2 times the energy divided by the mass. If we plug in 67.5 joules for the energy and 0.8 kilograms for the mass, we get an answer of very nearly 13 meters per second. What's the angular frequency? Omega is the square root of k over m. So this is the square root of 1,500 newtons per meter divided by 0.8 kilograms. Giving us an answer of 43.3 radians per second. Express the position of the system as a function of time. X is some sort of function of time. What is that? Well, we can say x equals a cosine omega t in general. Specific to this problem, then, x would equal 0.3 meters times the cosine of 43.3 radians per second times time. What's the period of oscillation? Period is equal to the inverse of frequency, and frequency is equal to angular frequency divided by 2 pi. So period is just equal to 2 pi divided by the angular frequency. So in this case, the period is 2 pi divided by 43.3. And this gives us a period of about 0.145 seconds. So somewhere between 14 and 15 hundredths of a second. Okay, hopefully that helps illustrate some of these equations that we've been deriving along the way and how you can apply them to some realistic problems.